So what we're going to talk about in this video is the empty set. We introduced sets in the previous video and you thought of them as things like a bag full of contents. It's actually a very general definition. The empty set might make sense. It is the bag with nothing in it. Right? It is the empty set. So this is an illustration of the empty set right here. And we typically use this symbol to represent the empty set. So we say if their set contains nothing, then the set is the empty set. And this set pops up surprisingly often. So an example is, I'm going to use the set property notation. I'm going to say D is the set of all x being real numbers such that x is less than 0 and x is greater than 5. All right, if we draw this on a number line, let's see that this is the set. This has to be here because x has to be less than 0, and there's an implicit and in this, and x has to be greater than 5. Right? So what areas overlap here? None. So this is the empty set. Okay, and it turns out that the empty set is kind of interesting. So let's take a look. So what I'm going to say is that the empty set is a subset of all other sets. That's what this theorem says. This empty set is a subset of S for all sets S. And to prove this, I'm going to use a proof by contradiction. Right? If you recall from previously in the semester, a proof by contradiction, you suppose the opposite. So I'm going to say, suppose not. Now, what does that mean? If I'm saying, if my statement is for all sets S, empty set is a subset of S, then my negation is that, well, maybe there's exists a set where the empty set is not an element or a subset of S. Now notice, this is actually a really important note here, and I should have been more explicit. We are saying the empty set is a subset of S. This is not saying that the empty set is an element of S. Right? These are two very different statements. So I'm not saying that somewhere in the bag or the set S, we have the empty set. What I am saying is that the empty set is contained within the set S for all S's. So negation is, remember, if you take the negation of a universal conditional statement, it becomes existential. So there exists a set, let's call it S prime, such that the empty set is not a subset of S prime. All right, so these are our negation here, or these are the statement and the negation. Let's separate that. Suppose not. Back to our proof. That is, suppose there exists some set S prime such that the empty set is not a subset of S prime. Right? Well, let's go back to the previous video where we defined subset and not a subset. And we gave a definition for what's not a subset. So, and for what is a subset. So by the definition, of a subset, this means there must exist some element in the empty set that is not in S prime. Because if you remember, we said if something is not a subset of another one, then if we said if A is not a subset of B, we define that by saying there has to be some element X in A that's not in B. So if we're saying that the empty set is not an element or is not a subset of S prime, then that means there has to be some element that in the empty set that is not in S prime. But there can be no elements in the empty set by definition. This is where we find our contradiction. Therefore, the empty set is a subset of S for all sets S. Right? So we're saying if the empty set is not a subset of S prime, well, then that means it's got to have something in it that's not in S prime. Right? That's the definition of not a subset. But there can't be any elements in the empty set. It's by definition empty. And so that's where we get our contradiction from. So we're using a technique here known as the element argument. To prove this. And that's where we look at the definitions of the sets, subsets, and so on, by considering elements that must or must not be in them. Okay, we're going to do several proofs using this element argument.